Hello, everyone, and thank you for joining us in today's sessions of Fundamental of Electronics. In today's session, we are going to take you through a really interesting and useful topic that's known as operational amplifiers, or in short, op-amps. Uh, Basically, in order to convey the concept today, we laid out the session in the following way. In the first section, we are going to explain what is op-amp in general. Then we will talk about the golden rules of op-amp that helps you to analyze all different possible of arrangements and configuration of op-amps. Uh, Thirdly, we're going to talk about an instrumentational amplifier arrangement, and we are going to use these rules in order to solve a very useful combination of op-amp arrangement or op-amp layouts that is known as instrumentational amplifier. Lastly, we are going to talk about some very important parameters of op-amps that are essential to know. And then we are going to introduce to you some references that can help you to understand the concept better. We will give you some time for your questions. And finally, we will have an overview for the next session. So let's start with the explanation of op-amp. What is op-amp? Op-amps are in general like an integrated circuit that can amplify low power electric signals. So it somehow resembles like a radio astronomy telescope that takes a really faint signal from a faraway star and it amplifies that signal and gives you a lot of meaningful information from that signal. So that probably can be considered as a really good example for what op-amp really does, but maybe on different types of signals, electronic signals. So basically, an op-amp consists of two input pins known as V plus and V minus, and one output pin known as VO or V out in different references. And we also have two pins to supply this device known as VCC and VEE. So these two pins are basically connected to positive supply rail and negative supply rail in order to turn on the device and make it functional. The gain of the op-amp is another important thing to know. The gain of the op-amp is something huge. It's something really close to infinity. And basically, it's like scaling. It scales up the voltage difference across V plus here minus V minus, and then it reflects this multiplication. Multiplication of that gain by this voltage difference to the output voltage. The other thing about the op-amp is the saturation. Actually, we really need to know that the device cannot give you infinite amount of voltage at its output voltage. There are some limitation, and that limitation is basically restricted by the supply voltage of the component. In another word, when V plus is larger than V minus, the output voltage tends to get closer and closer to VCC. It will be chopped by VCC. And when V minus is larger than V plus, the output voltage will be chopped by VEE or negative voltage, negative supply voltage. So that's basically what we have for saturation of these devices. That's really important to know. These are the most important things about the behavior and characteristic of op-amp to know. Now let's talk about the golden rules in op-amps. The first rule is forced equal input voltages. Basically, all the op-amps like to keep the input voltages, V plus and V minus, equal to each other. And that's a really interesting feature, really interesting functionality of this device, because whatever you apply on V plus, you can easily see it on V minus, and in reverse, if you apply something on V minus, it can easily reflect it back on V plus. The other thing is that the current will be blocked on input terminals. You wouldn't see any flow of current on input terminals. And that's because the huge amount of input impedance that we have on this device. And it gives you a lot of interesting feature, including a very precise like precise way in tuning the gain of the device. And lastly, the device has an impedance really close to zero, output impedance really close to zero. And the reason of it is that this device is designed to supply like maybe a high amount of load, or it's designed to power up the input signal and drive a lot of loads. And that way, we don't like to see any voltage drop, internal voltage drop on the device. And that's why we really like it to be as close as to zero. So now that we know all these golden rules, let's solve this instrumentational amplifier example. So basically, this is a layout that we have for an instrumentational amplifier. It has 3 amplifiers and some resistors. All of these components are usually inside the package, except for this R gain, which is a tunable resistor. It's outside the device. This arrangement has a lot of interesting features, including a high basically resiliency against common mode noises, because it has a very nice symmetry, and a lot of other things that unfortunately we don't have enough time to go through all of them. But let's analyze this configuration with the rules that we just have gone through. So we can split this configuration into 2 main parts: input stage and output stage. Interesting point about input stage is that you can see a very nice symmetry from the top and bottom of this configuration, basically in this stage. You can see R1 is here. Again, we have R1 here. We have 2 identical op-amps here and R gain in between. So basically from the midpoint here, we have a very nice symmetry. And we can basically fold this circuit on from that line to analyze the other part. So in order to do that, we can easily see that VI1 is equal to minus VI2 because it's a differential pair applied to the input terminals of this device. Same is true for VO1 and VO2. VO1 is equal to minus VO2. So what if we name VI1 equal to minus VI2 as VID? And what if we name VO1 equal to minus VO2 as VOD? So that way we can just analyze one simple side of this two-sided symmetric circuitry that is drawn here. So it's a really simple circuitry, and we know it as non-inverting configuration because the input voltage is applied to the positive input terminal or input pin. So let's apply the first rule, that is the equal amount of V plus and V minus, and that causes the reflection of VID because VID is equal to V plus and V plus is equal to V minus. So basically VID will be reflected back on V minus, and you will see VID here on this midpoint. That causes a flow of current here on this resistor, which is half of the R gain, and that makes a current of 2VD over R gain. The second rule says that there is no current in this input pins. So there's a blockage of current here. Therefore, whatever current that we have here in this branch would be flown on this branch. Very simple thing, isn't it? So by applying a very nice KVL here, we can easily find out the voltage over VOD. So VOD, which was VO1 equal to minus VO2, is equal to R1 multiplied by 2 over R gain, VID, which was this current, or let's say the voltage drop here, this current multiplied by R1, plus VID, this voltage. So this is a KVL that we are applying here. And that way, by just simplifying, by substituting VO1 instead of VOD, and VI1 instead of VID, or VO2 instead of VOD, and VI2 instead of VID here, we can easily find out the gain for the whole arrangement. So basically, in this arrangement, we have a difference voltage here and difference voltage here. So to expand this equation for the whole arrangement, we just need to substitute those values there, and we end up with this gain for the first stage. So now let's apply the same rule for the second stage. In the second stage, you can see we have the blockage of current and the equity between the voltages, and that gives us 2 voltage dividers on the top as voltage divider 1 and voltage divider 2 at the bottom. So for voltage divider 1, we have a flow of current IO1 prime here, which is equal to VO1 minus VO plus over R2, and we have IO2 double prime, which is equal to V basically plus minus VO over R2, R3. So this is the flow of current like this here, and we know that there is no flow of current here, therefore IO1 prime is equal to IO1 double prime. And from this equation we can see the right hand side of these two equations can be equal, and from that we can find V plus. So V plus is equal to R2 over R2 plus R3 multiplied by VO plus R3 over R2 plus R3 multiplied by VO1. So from voltage divider 2, we can easily find this voltage through this equation, R3 over R2 plus R3 multiplied by VO2. And based on the fact that we have from the first law that V plus is equal to V minus, we can simplify, put the right hand side of this equation here and make them equal to each other, and from that we can find the overall gain of the second stage, and here's the overall gain of the second stage. So the last thing is just to merge up these two stages like this, and we can actually find the overall gain of the instrumentational amplifier like this. So we saw how these golden rules can help us to easily analyze all different types of arrangement and configuration of op-amps that includes the instrumentation amplifier. That's really useful for different applications. So the next thing is to take you through some very important parameters and concepts of op-amps. So some of them are listed here, and I strongly recommend you to go through them and understand them properly, because they're really vital to understand how an op-amp works. So the first one is unity bandwidth, the other one is slew rate, the other one is common mode rejection ratio, supply voltage rejection ratio, input offset voltage, and input offset current. And here are some references that are really useful for you guys. Please go through these references, try to solve as much as possible of questions, and if you had any question, please ask your questions. Later on I show you my email, and you can actually send through your emails to me, and I would be more than happy to help you with all your questions. So these references are really useful, and please have a look at them and try to get yourself familiar with this concept. Here is my email, and feel free to ask any question if you have. And finally, we can go through an overview for the next session. Thank you very much, and that was amazing having you all in this session, and feel free to get back to me if you had any question, and feel free to send me your email, for whatever question or whatever concern that you may have for this session. Thank you very much, and have a lovely time. Bye.